Welcome to session 04 of the Celery series. Today we tackle a modern challenge, running GPU-intensive AI inference tasks on a Celery cluster without crashing from out-of-memory errors. LLM text generation, diffusion image generation, and embedding extraction are extremely GPU-intensive. A dedicated GPU like the NVIDIA A100 has a hard VRAM limit. If workers process tasks concurrently without any control, GPU out-of-memory errors can immediately bring down the entire processing cluster. The solution is a specialized GPU queue orchestration model. AI tasks are routed to separate queues by priority and required GPU. High-priority LLM inference runs on workers connected to a 100 GPUs with concurrency set to 1. Lighter embedding tasks go to cheaper T4 GPUs using Jevon pooling. A cleanup queue runs periodic maintenance on CPU. Start by declaring task routes in your Celery configuration. Each task name maps to its dedicated queue. Then launch separate worker processes, each listening only to its assigned queue with the appropriate concurrency and pool type for the underlying hardware. Multiple workers connected to the same GPU can exhaust VRAM by loading different models simultaneously. The fix is a Redis distributed semaphore. Before running inference, a worker must acquire the GPU resource lock using the atomic set nxpx command. If another worker holds the lock, the task retries with a short countdown instead of blocking. The time to live is a safety net. If the worker crashes mid-inference, the lock still expires. Loading a large AI model from disk into VRAM can take 30 to 60 seconds. To avoid loading it for every task, a worker marks the model as warm in Redis after a successful load. Later tasks requesting the same model are routed to the worker that already holds it. A periodic Celery beat task scans for cold models with no recent requests and unloads them to reclaim VRAM. For LLM text generation tasks that must return output token by token, waiting for full completion before writing to the result backend is impractical. Instead, the worker continuously publishes tokens to a dedicated Redis PubSub channel. An API server like FastAPI subscribes to that channel and streams results to the browser through server-sent events or WebSockets. We have explored GPU queue orchestration with specialized routing, distributed semaphore locks to prevent VRAM exhaustion, model warm-up caching with periodic cleanup, and streaming inference results over Redis PubSub. Session 05 will cover operations, monitoring, and troubleshooting in production.